There are several properties of limits that enable us to calculate limits efficiently. For example, if we have a constant function, for example, the constant function that always outputs a 7, then if you take any limit, the result will just be that constant. That's what this rule says. Another rule is that if you have the function f of x equals x, that is the function that outputs the same number you input, then when you take a limit letting x get closer and closer to a, the outputs also get closer and closer to a. If you take a limit of a sum, you can calculate that from the sum of the limits. And we're about to see an example of this in action. Similarly, if you have a limit of a product, then you can just evaluate the product of the limits. So here is an example. Suppose that we want to calculate the limit as x approaches 2 for the function x squared plus 3x. Because we have a sum inside the limit, one of the properties we just looked at says that we can calculate those two limits separately. So we'll have the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 3x. Then I can use the other property that allows us to break up a product. So, for example, over here where we have the limit as x approaches 2 of 3 times x, I can change that into the limit as x approaches 2 of 3 times the limit as x approaches 2 of x. And I can do the same thing with the x squared here by thinking of this x squared as x times x. Doing so allows me to write this as the limit as x approaches 2 of x times the limit as x approaches 2 of x. Now we can use those first two properties to finish simplifying. One of the properties said that since the function is x, that is to say it outputs the same thing that is input, if x is approaching 2, the output also approaches 2. So both of these limits approach 2. So does the very last limit. And then here we have a constant function. As x is approaching 2, the outputs approach 3. They actually stay at 3. So if you simplify this, 2 times 2 plus 3 times 2, the result is 10. We've just calculated the limit of this quantity. And that's without having to resort to a graph or a table. This approach is much more efficient than having to use a graph or a table once we know how to use these properties. Let's go back to our list of properties and add one more. You can also calculate the limit of a quotient, meaning one function divided by another function, in more or less the same way, but there's one point that we need to be careful about. The limit of the denominator can't be 0, otherwise we'd be dividing by 0, and we know that that's not allowed. So here's another example. We can calculate the limit as x approaches 3 of x plus 1 over 2x plus 1 by taking the limit of the numerator divided by the limit of the denominator. And then if you calculate each of these limits using the same approach that we did in the last example, you're going to end up with 3 plus 1 for the limit in the numerator, and 2 times 3 plus 1 for the limit in the denominator. And the total result can be simplified as 4/7. Looking at these last two examples we calculated leads us to a conclusion that will make it even easier to calculate a lot of limits. The first example was for a polynomial function. That's anything that can be written in this form. A coefficient times a power of x plus a coefficient times another power of x, and so on. In fact, you can think of this last term as a coefficient a subscript 0 times x to the 0. And it turns out that any polynomial function is easy to work with when you're trying to calculate a limit. if you want to calculate the limit as x approaches a in a polynomial function, all you really have to do is plug in a. Rational functions are functions that are written as one polynomial divided by another polynomial. The second example we worked was a rational function. And if you go back and look at that example again, you'll see that the answer we got is what we would obtain by just plugging in what x is approaching. And we can do that whenever the denominator is not 0. So here's one more example to illustrate how this can make things easy for us. In this case, we want to calculate the limit as x approaches 0 for 2x squared plus 3x minus 1 divided by x squared minus 4. And it turns out all we have to do is plug in what x is approaching because this is a rational function. The numerator is a polynomial and the denominator is a polynomial. So if we do that, we get 2 times 0 squared plus 3 times 0 minus 1 divided by 0 squared minus 4. Now, we do need to make sure that our denominator is not 0 if we're going to use this approach. And in fact, it's not. 0 squared minus 4 will simplify to negative 4, which is not 0, which means we're fine. If we finish simplifying, this becomes negative 1 over negative 4, or 1/4. And that's the final answer. So, using the properties of limits can make it a little bit easier to calculate a lot of limits for polynomial functions and rational functions especially.